Maybe before I start, I just want to thank Jesus and Juan Carlos for the invitation. It's very nice to speak for UNAM. And
Uh,
today I want to talk about some new result that we obtained in joint work with Jiayin Pan at UC Santa Cruz and Xing Yuzhu at Michigan State University. So today I want to talk about Ricci curvature results. I want to talk about their topology under special volume growth assumption. So maybe a few words about the plan of this talk. First, I didn't want to assume too much about Riemannian geometry knowledge from the beginning, so I'm going to reintroduce some curvature definitions so everyone's on the same base. I also want to reintroduce a whole array of historical results about what we can say on the fundamental groups of manifolds when their Ricci curvature is either non-negative or positive. So that's going to be more of a historical part. What can we say? And I want to introduce the main result, and I'm going to spend some time sketching the proof of theorem A. I try to add a lot of pictures to give more rough of an idea of what is going on without going too much in the details. And I'll be happy to go into more details if we have time at the end. Then we also have some counterexample and open questions, so I hope to have a little bit of time to go through a few of these. So first, let's talk about curvature, and maybe let's talk about the first type of curvature that you see in a Riemannian geometry course. So first, let's say we have Mg, that's the notation I'm going to take for a Riemannian manifold, smooth Riemannian manifold, and let's say you fix a point P in your manifold and unit split geodesics that are orthogonal at P. So what I mean by this is we have our point P, I have a geodesic alpha that's unisplit, geodesic beta that's unisplit, and the angle their velocity make at the point P is pi over 2. They're orthogonal. So something I want to look at to define the sectional curvature is I want to look at my geodesic alpha. I run through this geodesic for some time t, end up on a point alpha of t. I do the same thing with beta. I get a point beta of t, and I want to look at this distance precisely. So the distance between alpha of t and beta of t. And in some sense that I'm going to give you in a second, the sectional curvature is going to tell you how this distance is evolving. So more specifically, you have the following Taylor expansion of this distance. So this distance, as you can see, is a function of t. You can look at its Taylor expansion at time t equals 0. And the first term that you have is square root of t. So the square root of t is exactly what you would have if you were in the Euclidean space. If you were in the Euclidean space, take two orthogonal geodesics, unit speed, look at the distance between them. This is exactly the Pythagorean theorem. However, in a Riemannian manifold, it's not necessarily Euclidean. You have some curvature. And the curvature terms appear here. So you have a term kappa over 12 times t squared. And this kappa is exactly how you define the sectional curvature at the point P of the plane spanned by alpha dot 0 and beta dot 0. In other words, the velocities. So something you can see is that if kappa is equal to 0, then you're almost like the Euclidean space. If kappa is positive, then this distance, as on this picture, doesn't grow quite as fast as in the Euclidean space. So that's something you may see on a sphere, for example. And on the other hand, if kappa is negative, then this term is bigger than 1, and the distances grow faster than in the Euclidean space, something you may see in the hyperbolic space, for example. So in other words, the sectional curvature measures the infinitesimal defect in the Pythagorean theorem. It tells you how flat your space is, basically. So that's it for the sectional curvature. It tells you something about distances. So, but something I want to talk more about today is the Ricci curvature. So let me first define it. Say we have a point P in our smooth manifold and a unit vector that I'm going to write U in the tangent space to M at P. The first thing you want to do before I get to this formula is you want to fix vectors E1, E2, all the way to En minus 1, such that together with U, they make an orthonormal basis of TPM. So we have n vectors. I'm defining the Ricci curvature at the point P of the vector U with itself to be the sum of the sectional curvature of all the planes spanned by U and one of the other vectors of the basis. Okay? So the Ricci curvature is kind of an average of all the sectional curvatures. A small remark here is that you see I have like some kind of a basis that's fixed here, and I only have U in the formula. This quantity over here doesn't really depend. It doesn't depend on the choice of the family that you use to complete U into an orthogonal basis. Okay, so that's the Ricci curvature. So you can think of it as an average of sectional curvatures. Something I'm going to be more interested about today is lower bound on the Ricci curvature. So let's first define what this is. Say you pick a real number k, we're going to say that the Ricci curvature is at least k if for every point p in my manifold and every unit vector u in TPM, I have the following inequality. The Ricci curvature at p applied to u is at least k. Another interesting inequality is the strict inequality, defined in exactly the same way. I just replaced the large inequality by a strict inequality over here. So these are the curvature objects that I'm going to use today. So something I was saying is that the sectional curvature tells you something about distances. Ricci curvature is not quite as strong. It doesn't tell you something about the distance. It tells you something about the distance and the volume. So in other words, it measures the distance volume interplay. So it's kind of a maybe not too rigorous word to say like this. So I just included one very important theorem to illustrate this idea. And this theorem is Bishop's inequality. So this theorem goes as follows. So say you take a Riemannian, yeah, Omar?
Hi, good morning to
Yeah,
everyone.
good morning.
This definition is taking a unit vector. In general, you can think of the Ricci tensor in general, and then specify the definition for this unit vector, or is different.
Yeah, so the idea here is that this is actually, you can actually define a bilinear form using this. So if you want, you can define Ricci of U V by using the polarization identity on this. So this is the quadratic form, and Ricci of UV would be the bilinear form. So you don't have to pick the same vector everywhere, but today I want to talk about lower bounds, and in lower bounds, you do define it with only picking one vector. So this definition is a bit easier to state, but
Okay.
yeah, you're correct.
In general, no, we can take the in general the tensor.
Yeah, you can.
Vale. Thanks.
No, no problem. Yeah, everyone, like, feel free to ask questions if I skim too fast over anything. So yeah, there's this inequality, which is telling you that if you pick a complete Riemannian manifold with non-negative Ricci curvature, dimension n, then for every point p and every radius r, the volume of a ball of radius r centered at p is at most the volume of a ball of radius r centered at 0 in the Euclidean space. So what this is telling you is that if the Ricci curvature is bounded from below by the Ricci curvature of the Euclidean space, so in other words, 0, then the balls in your manifold, they don't grow quite as fast as in the Euclidean space. Okay? So in other words, Ricci tells you something about the distance. You need the distance to define balls. And it tells you something about the volume. So it's the distance volume interplay. Maybe a small remark here. I stated for Ricci non-negative. You also have versions for any Ricci lower bound. If instead of Ricci non-negative, I have Ricci bounded from below by 1, the balls are not going to grow quite as fast as ball in the sphere of dimension n. If instead of 0, I had -1, the balls are not going to grow quite as fast as in the hyperbolic space of the same dimension. Okay? So that's the way you can sort of think of the Ricci curvature. Instead of telling you something about the distance, it tells you something about distance and volume together. Okay? So maybe now I want to talk a bit more about topology, right? So the general question you may ask yourself is pick any smooth manifold. Let's call it Mn. And the question is, for example, are there any Riemannian metric G such that Ricci of G is bounded from below by 0? So That's the question. You fix a topological space, smooth manifold. Are there any metric that satisfy this assumption? So in other words, you want to say another way to formulate this question. So maybe say this is question one. Another way to formulate this is if I know that Mg has Ricci non-negative, what is the topology of M? So if I take a Riemannian manifold, non-negative Ricci curvature, I want to be able to say as much as I can on the topology of the smooth differentiable manifold a priori. Okay? So first of all, why are we going to focus on pi1 in this talk? That's because of an important theorem of Bengui, which is the following. So there is some Riemannian manifold with positive Ricci curvature that have infinite second or higher Betti numbers. So in other words, if you only assume positive Ricci curvature, no additional assumption, it's going to be very hard to say anything about Betti numbers for the terms that are bigger than one. They can be infinite. You're not going to be able to state anything about them being bounded. So of course, this is stated for open manifold, but that's the manifold we're going to care about in this talk. So the question I want to ask now, and that's the question we're going to study during this talk, is given a Riemannian manifold with Ricci non-negative or Ricci positive also, what can we say about its fundamental group? So first, there's two cases. There's the compact case, the non-compact case. I want to start with a few important results on the compact case. And for this slide, I'm going to pick a closed Riemannian manifold. So by this, I mean that it is compact, does not have a boundary. Okay. So there's two very important results, which I stated slightly differently than the way you may have seen them, but these are basically corollary of the important results. So first, there's this result of Chico-Gromol in 72, which tells you that if the Ricci is non-negative and you are closed, then the fundamental group is virtually abelian. So that's a word we're going to see a lot. What this means is that the fundamental group admits an abelian subgroup of finite index. So in other words, it means that your fundamental group is, if you forget about a small part of it, it's basically a group of the form z to the k, an abelian group. Okay? So in other words, you're not going to see groups that don't admit any abelian subgroups of finite index. We're going to see some of these groups a little bit later. So that tells you a lot already. Another important theorem is the Bonnet-Myers theorem, which is telling you that if Ricci is positive and you are closed, then the fundamental group is finite this time. Okay? So these are sort of the two key results that I'm gonna keep going back to during this talk. But this is the compact case. What you may wonder is what can we say in the open case? So by open, what I mean is complete, non-compact Riemannian manifolds. So let's see what we know about open manifolds. So to do that, I'm going to have to introduce a notion. I wasn't sure whether everyone was familiar with this, so let me just define it and maybe give a few examples. So we talked about abelian group for closed manifold. We're going to need to talk about nilpotent groups for open manifold. So what's a nilpotent group? A nilpotent group is a group such that there is some integer k, such that the group nk is equal to the identity. What's the group nk? You want to define it iteratively. So first you define n0 to be the group itself, and then to pass to the next step, to define n I plus 1, you take a commutator of n with the group that was before, with ni. So this is a normal subgroup of n. So maybe a quick remark here. Imagine your group was actually trivial group. In this case, n0 is equal to 0 immediately. You're done. It is nilpotent. Second most easy example, your group is abelian. So maybe this guy is not 0, but if you take n1, which is the commutator of n with itself, then this is 0 immediately. So an abelian group is going to be nilpotent as well, and the k over here is going to be 1. So now if you take something a bit bigger, a general nilpotent group, you can think of it as the next best thing compared to abelian group. If you take one commutator, it may not be zero, but if you take sufficiently many commutator, at some point you will get zero. And this sufficiently many number is this number k over here. Okay? So slightly larger class than, I mean, much larger class than just abelian groups. So maybe let's see one example, an important one, which is the discrete Heisenberg group, usually denoted H3 of Z. So I'm going to write it N because it's nilpotent. How is it defined first? You want to look at the matrices with one on the diagonal, zero below, and integer coefficients outside of the diagonal, above the diagonal. So you want to see this group is nilpotent. So what you do, you take N and you take its commutator with itself. So doing that, you get a group N1, and that's an exercise. I'm not going to do it now, but that's not too bad of an exercise. If you take the commutator of N with itself, you're going to get the same thing. However, the coefficient A and B are going to turn out to be zero. So you only get one term outside the diagonal. And the next thing you do, you want to take the commutator of this N1 back with N itself. And if you do that, what you get is you get the trivial group. In other words, the Heisenberg 3 group is nilpotent, and its nilpotency step is this number 2. Yeah, Omar?
There is some example in physics about this group, Heisenberg group. In some sense, it tells you that the operator it reduced to zero, no?
Mm,
If you think
so,
as an operator, as in quantum mechanics, so it tells you that it reduced to zero in some sense. But
so
I don't.
something that is true is that say you take a compact Lie group, for example, say it's connected and nilpotent at the same time, you can look at its Lie algebra, and what you're going to be able to say is that taking a Lie bracket with an element of the Lie algebra is going to be a nilpotent as an endomorphism. And if your group is compact, being nilpotent, you can fix also some scalar product on your Lie algebra that is invariant under your whole Lie group. And you're going to get basically, you're going to see that bracket X, there you can write it like this, also add of X. You're going to see that this is antisymmetric and also nilpotent. And if that's the case, then you have to be zero. So you have to be abelian.
Yeah. I
But
was
yeah,
thinking
I think
about
maybe this is what you.
something like that. I was thinking about the Pauli matrix. I don't know if this.
Oh
If
yeah,
this.
the polymatrix. Yeah, the polymatrix are going to be generators of. I'm not sure whether it's exactly the same. I think polymatrix are for SL2Z, no, maybe.
For SU2, I
Oh
think.
yeah, SU2. Yeah, you're right. Yeah,
Okay, something like that. I don't see
yeah.
very well in terms of operators, but it
Mhm.
tells you that in some sense it's reduced to trivial. But I don't know.
Yeah, you can do a lot of group theory with this assumption.
Okay.
But that's one example. There's a lot of other examples of nilpotent groups. For example, you can take the quaternions. Some dihedral groups are going to be nilpotent. Some of them are not going to be nilpotent. SL and Z is never nilpotent. You have most of the groups you have in mind, we know whether they are nilpotent or not.
Okay.
So an important remark is that thanks to Cheeger-Gromov, if you remember, if you're a compact manifold with non-negative Ricci, fundamental group has to be virtually abelian. So there's another group theory result, which is telling you that if you take a non-abelian, nilpotent group that doesn't have any torsion, then this is never virtually abelian. So in other words, you can see Cheeger-Gromov's result as telling you, for example, that the Heisenberg 3 group is never going to be the fundamental group of a closed manifold with non-negative Ricci curvature. So take any group that is non-abelian, torsion-free, nilpotent, it's never going to be such a fundamental group. Before I move on from fundamental group, I just want to mention one result because I'm going to use it later. And that's a group theory result. I don't know the exact proof, but I gave a small reference here. I can send the slide after, by the way, anyone is interested. But that's the result we're going to use in a little bit. If you take a nilpotent group that is finitely generated, then it admits a finite index subgroup, let's call it H, that admits a central series with infinite cyclic factors. What do I mean by this? I simply mean that I have something like this. So I'm sorry for the lambda here. It should be n. Let me go over it. It should be H. Sorry, it should be the group H that I introduced over here. So saying H admits a central series with infinite cyclic factors means that I have my group H, call it H0, H1, normal in H0, and I continue, decrease, and eventually I get the trivial elements. Something I want is that the successive quotients are the group of integers. So don't worry too much about this result. We're going to use it a little bit later when I give a sketch of the proof of the main result. So that's nilpotent groups. They play a big role in the case of open manifold. So let's see why. So now let's study open manifold, and we're going to start with this very important result of Milner and Gromov, which go as follow. So if you take an open manifold with non-negative Ricci curvature, and if you take a finitely generated subgroup, I'm going to write it always like this in this talk, f dot g, of the fundamental group, then such finitely generated subgroups, they're always virtually nilpotent. Okay? So this time we lose a little bit, not virtually abelian, but virtually nilpotent. So something you may wonder is, could we actually prove that not only they're virtually nilpotent, they're virtually abelian? And the answer is no. And that's because of a result started by Wei and finished by Wilking, which is the following. If you take any finitely generated virtually nilpotent group, this group is going to arise as the fundamental group of some open manifold with positive Ricci curvature. So in other words, any finitely generated group is going to be some fundamental group of an open manifold with positive Ricci. So after his theorem, Milner conjectured the following, which is that he thought that the fundamental group of an open manifold with non-negative Ricci is always finitely generated, because all the examples we had in mind, that was the case. And it took a very long time to solve this conjecture, almost 60 years. And that was very recent work. And that's a new theorem by Bluey, Neighbor, and Semola, who disproved Milner's conjecture for dimension at least 6. So the theorem is as follows. If you take any dimension at least 6, there is some open Riemannian manifold with non-negative Ricci curvature and this dimension n, whose fundamental group is Q mod Z. So that's a group that is not finitely generated, but it arises as the fundamental group of an open manifold with non-negative Ricci curvature. Okay? So Milner's conjecture is false, but then you're like, okay, we don't even know whether fundamental groups of this manifold are finitely generated. That's kind of a basic assumption for group. What can we say if we can't even say this? Then this is difficult. So you may be like, okay, like if we don't assume anything else than Ricci curvature bounded from below, it's going to be hard to say anything about the fundamental group if we don't even know it's finitely generated. So something you may wonder is, can we add some constraints so that at least we know it's finitely generated under these constraints? And a possible answer to this idea is the notion of volume growth. So let me give you a quick result. Say you take a manifold, open, a non-negative Ricci, then we have the following property, and this property is just because of the Bishop estimate I give you at the beginning of the talk. So if you take a ball of radius r centered at a point P, divide by r to the power n, and take the limb sup when r goes to infinity, this quantity is always finite. And that's because if the Ricci curvature is non-negative, the balls, they don't grow as fast as balls in Rn. So just taking this inequality exactly tells you this. So we have an extremal case. The volume growth is at most like in the Euclidean space. So that's the maximal case. We also have a minimal case, and that was proven by Calabi and Yao. And it's telling you that if you take the same thing, volume of ball of radius r, but instead of dividing by Rn, you just divide by r this time. And instead of taking lim sup, you take lim inf. This quantity is always positive. So another way to say this is that the volume growth is at least linear. So it's at least linear, at most Euclidean. So now we have some properties, two extremal case, Euclidean, linear. You may wonder, okay, if I assume one of these, can I say a little bit more about the fundamental group? Can I at least know it's finitely generated? So we have this result of Lee and Anderson, which tells you that if Ricci is non-negative, and if instead of having this guy over here, I take the limb inf, so if the volume growth is exactly Euclidean, then the fundamental group is finite. So that's very good result. It's telling you a lot about the fundamental group. Has to be finite, in particular finitely generated, virtually abelian, anything you want. So this is the best you can get. If your Euclidean volume growth is basically done. In the other limiting case, so that was a result of Sormani, if Ricci is non-negative and you have linear volume growth, so in other words, the volume growth is at most linear, so this is the condition, then the pi1 is finitely generated. So at least Sormani proved that Milner's conjecture is true if you assume the linear volume growth of your manifold. So we know that with linear volume growth, you're finitely generated. Can you say a little bit more? And that's what's going to bring me to the main results. And let me present them now. So the assumption that we're going to look at now is M is an open Riemannian manifold with linear volume growth. So I assume that the lim sup of the volume of ball of radius r divided by r is finite. So the first result that we obtained with Jian and Xingyu is that if the Ricci is non-negative, then pi1 is virtually abelian. So you can see this first result as sort of an extension of Chigo-Gromol's results. I was telling you if you're closed non-negative Ricci virtually abelian, this is an extension of their result to the case of open manifold, but in the minimal volume growth case. So that's the first result. The second result is an extension of Bonnet-Myers, which is telling you that if Ricci is positive, then the pi1 is finite also. So we had Bonnet-Myers telling you if you're closed with positive Ricci, pi1 is finite. Here it's one more step, sorry. It's one more step compared to being closed. You're open, but with minimal volume growth. So any questions so far? Yeah.
Virtually abelian was about this change condition about the subgroups and the normal quotient. It's trivial. Or what is virtually
Sorry,
abelian?
the virtually abelian, it means that, let me write it again. It means that there exists, there exists a subgroup H in pi1 of M such that H is abelian and the quotient of pi1 modulo H is finite.
Finite.
Finite. Yeah. Any other questions?
No, I don't think we have any further.
Okay. So let me. So now what I want to do is explain the tools we use to prove theorem A. So first of all, let me just take the assumption. So we take M, open manifold, Ricci non-negative, linear volume growth, and the notation I'm going to use for this whole sketch is big lambda is the pi1, okay? So there's going to be a bunch of notations. If you lose track, please let me know. First thing we're going to want to do is people proved a lot of things on the pi1. We're going to use as much as what they proved to reduce the fundamental group of our manifold to make it maybe a little bit more handleable. So first of all, if you remember, Christina Sormani proved that Milner's conjecture holds under this condition. So we know that big lambda is finitely generated. And we also have the result of Milner and Gromov, which tells you that finitely generated subgroups of pi1 have to be virtually nilpotent. In particular, if the pi1 is already finitely generated, then it is virtually nilpotent. So at this point, lambda is a finitely generated virtually nilpotent group. And we had the result, if you remember, at the bottom of the slide on nilpotent groups, where I had like a some sort of a series of a subgroup where the successive quotients were the group of integers. That's exactly what I'm going to use. The conclusion of these two results and this group theoretical result is that replacing M by a finite cover, if necessary, there is a series of normal subgroups. So lambda is the first one. I'm going to call it lambda 0, smaller one, lambda 1, and it decreases lambda k minus 1, eventually lambda k equal to identity, such that each successive quotient, lambda j mod the one that's coming after, is the group of integers. So that's already something quite important about the pi1. It's been reduced to a central series where each quotient is the group of integers. Something else that you also know that's a fact from algebraic topology. If you take a subgroup of the fundamental group, if you take the universal cover quotiented by this subgroup, you get a cover of your manifold. So that's exactly what we're going to do. We're going to look at the universal cover, M tilde, over here, quotiented by each of the mj, by the lambda j's. So let's call this quotient mj. So M tilde is the first one. Over here, it corresponds to M tilde quotiented by the identity. So I have this guy. This guy is going to project on M tilde quotiented by the second smallest group, mk minus 1, which is going to project on mk minus 2. So on and so forth, until I end up with M1 projecting on M0. M0 is M tilde mod lambda 0, which is in other words, M tilde quotiented by pi1 of M. And you know that the fundamental group quotiented by the pi1 is the manifold itself. So now we have this tower of successive covers. And if you take any cover here, the group of deck transformation is exactly going to be the group of integers because of the property we have above. So we have this tower of successive Z covers. The reason why we do this is that a Z cover, so where the group of deck transformation is the group of integers, they're much more easy to handle than any cover. Z, the group of integers, is the most simple infinite group you could ever have. So now the strategy of the proof is going to be as follows. We're going to want to look at each of these spaces one by one and look at their asymptotic geometry. So what I mean by this is we're going to start with this guy, so M, and we're going to want to see, I have M. I want to say, what does it look like when you look at it from a very far distance? So we're going to start with M0, see what we can say, then do M1, see what we can say, climb all our way up, to eventually be able to say something about the asymptotic geometry of the universal cover. So let's start with M0, okay? And I'm gonna give you a small picture to see what this is like. So maybe let's take a first example. If you take a manifold with non-negative Ricci, linear volume growth, maybe the simplest example you could think of is a cylinder, right? This has linear volume growth, it's flat, and it has linear volume growth. So start with this. I want to take this cylinder and imagine that I'm going to be looking at it, but from a distance. I want to see, I want to go further and further back. So I want to zoom out. If you zoom out from this cylinder, it's going to look like a narrower cylinder, right? Like this. And if you zoom out even more and even more, eventually it's going to be looking more and more like a thin line. So in other words, in the limit, it kind of looks like the real line R. So that's the first example. Maybe let's do another one. Another example of a metric with non-negative Ricci and linear volume growth is you could imagine some sort of a cigar metric on R2. So something like this. So I have my cigar metric. If I look at it from a distance, same thing, it's going to be a narrower cigar metric. And at the limit, when I'm very, very far, it's going to look like a half line. So that's the picture we have in mind. If we take linear volume growth, non-negative Ricci, we expect that when seen from a distance, they should look like one of these two cases. So not too rigorous right now, but so let's be a bit more rigorous. What do we mean by zooming out? zooming out, the way we formalize this in Riemannian geometry is you want to pick a sequence of rescaling that goes to infinity. So the more rescaling you take, the furthest you are. And zooming out means looking at your manifold rescaled by this Ri minus 1. So we have a sequence. The first one is our manifold. Ri minus 1 is seen from a distance. And as you increase the integer of your sequence, you're getting further and further. And something we'd like to say is that these rescalings, they converge to the real line or they converge to the half line in some topology. But to make this rigorous, we need a topology where the objects are metric spaces. In other words, to make sense of this convergence, I should be able to define a precise notion of, if I take two metric spaces, how far are they from one another? And there's a very good notion to do this, and that's something that was introduced by Gromov. It's called the Gromov-Hausdorff topology. And it's exactly this. It gives a precise meaning to converging sequences of metric spaces. You can say that sequences of metric spaces approach a certain metric space if the distance between them goes to 0. And using this terminology, Christina Sormani was able to prove rigorously that this rescaling in the Gromov-Hausdorff topology, they either converge to R or the half line. So thanks to this result, we know everything about the asymptotic geometry of the first step, M. We know either it's going to be a line or a half line when seen from a distance. So now that we know that, we can try to go one step further. We had a M1 that was covering M. So let's try to say something about the asymptotic geometry of M1. So I'm going to take the picture of the cylinder because it's nice and easy. So we have our manifold M. So think of it as a cylinder, right? And M1, yeah, Omar?
Sorry for the
Oh, don't worry.
but when you say you are scaling the M, you are saying that you are scaling the distance or scaling the metric or
That's
scaling?
a good question. So this guy here, you can think of it as either Ri minus 2 times the Riemannian metric G or Ri minus 1 times the Riemannian distance, dg. Okay? It's
Yeah.
the same. It's going to be the same thing. If you rescale by a square, the Riemannian metric, you're going to rescale by the normal thing, the distance. So yeah, good question. I'm rescaling the distance.
Okay. See, I was thinking about the rescaling himself the points of the manifold, but it is going to be difficult in some sense. I don't know.
Yeah.
If there's some global function in the manifold or something like
No,
that.
that's a good question. And yeah, I feel like it was going to be hard to introduce all the definition. I have some slides ready to define Gromov-Hausdorff topology if you're interested after, and I can introduce this more rigorously. But I more want to give a big picture. But I'm happy to talk about it more after if you want.
Yeah, it is just for the fluence of the talk.
Yeah.
Thanks.
But okay, so now we want to study the asymptotic geometry of M1. What is M1? It's a Z cover of our manifold. So in this picture, I have a cylinder. A Z cover is going to look like something like this, right? It's going to look like R2. Fundamental group of the cylinder is Z. So I have a group of integers Z acting on my cover, M1. I fixed a point P over here. Let's say the point P1 projects on P. Something that's going to be important for us and that we want to look out for is we want to look at the orbit of this point P1 under the action of the group Z. So I have P1, I have orbit points. In the case of this example here, the distance between two orbit points is going to be exactly the perimeter of this circle. Okay, so that's the first step. We haven't zoomed out yet. So now we want to zoom out. If I zoom out M, something we said is that it's going to be a narrower cylinder. So I get my Ri minus 1N looks narrower. So what does this guy should look like when I zoom out? Should look like the Z cover of this little space over here. So I have my metric space, Ri minus 1 M1, which is zooming out from M1. Still have the group Z acting on it, but this time the points in the orbit points of P1 under the group action of Z are going to be much closer from one another because I'm looking at them from much further. Then you can be like, okay, so what should this be like in the limits? In the limits, this guy here are going to go to a certain metric space. Let's call it big Y. The action of this group G is going to go to the action of a group G on this metric space Y. And these orbit points, ZP1 should go to the orbit of this little point Y under the big group G. So something you can see on this picture is that these guys were getting closer to each other. If you go from a very long distance, it looks like the orbit points are a continuum. Something that we can actually say, even one more thing, we knew that these guys were converging to something. And this thing that they converge to should be the quotient of this space by G. So that's my next slide. We knew that this guy was the quotient of this guy by Z. Same thing here, this guy is the quotient of this guy by Z. So this guy over here is the quotient of this limit by the limiting group action G. Okay? So we know that not only M1 is converging to a metric space Y on which a group G is acting, we also know that the quotient is isometric to either a ray or a half line, thanks to so many results. Okay? So on the picture, this looks like a continuum. We actually have more, and we're going to admit this. This is maybe the most technical part of the paper. The orbit GY is a line. So what I mean by this is that it's isometric to the real line. Okay? And we can use this fact because Y, the limit of M1 with rescaling, it's not any kind of random metric space. It's what you call a Ricci limit space. It's a limit of Riemannian manifold with a lower bound on the Ricci curvature. And there was a lot of work on these spaces. In particular, Chico and Colding, they proved the following result, which is a splitting theorem. If Y contains a line, then Y has to be isometric to R cross Z for some metric space Z. Okay? So we know this. We know something else. Maybe for simplicity, let's assume that the isotropy group at the point little y is the identity itself. We can also do the case where it's not, but it's more simple in this case. In that case, my group G is going to act by translation on this R factor, and it's going to act trivially on Z. And that's enough. Using this, I can see Y mod G is the same thing as quotienting this product by G. But G is acting trivially on Z, translation on R. So R mod G is just a point, and therefore I get that Z is isometric to Y mod G. In other words, thanks to Sormani's results, Z is either a real line or a half line. And therefore, we get the following conclusion, that is, Y is isometric to either the Euclidean plane, R2, or the Euclidean half plane, R cross R non-negative. Moreover, this orbit is going to correspond to one of the R factor. So either the first R factor in R2 or the R factor in the half space. So now we know the asymptotic geometry of M1. And we kind of developed a strategy that, given the asymptotic geometry of a space, we're going to be able to study the asymptotic geometry of its Z cover. So the next step is, instead of doing M1, we want to do MJ, right? Like every element in the tower. And we obtained the following result, which is an induction theorem, which is telling you that for each J, our MJ rescaled by our sequence of Ri minus 1, looking at the group action Z, is going to converge to a metric space Y, on which a group G is acting, such that Y is either a Euclidean space, Rj plus 1, or a half space, Rj cross R non-negative. Moreover, the GY is going to be a R factor. So let's see how we use this to conclude, and then I'll move on to some open problems maybe. So let's see how we conclude from this, and to do that, we need another notion, which is called the escape rate. That's something that was introduced by Jain Pan. And say I denote pi from n tilde to n, the universal cover. I have my point P tilde, a point in the fiber. So my P tilde is just over here. Now I take an element gamma in the fundamental group, which is acting by deck transformation. So it sends p tilde to a point gamma p tilde. And I denote absolute value of gamma, the distance from p to p tilde. So this distance over here. Given these 2 points, there's always a minimal geodesic joining them. And I want to define the size of this geodesic, the smallest radius, such that this geodesic is in the deck transformation applied to the ball of radius r. So for example, here, you can see that the entire geodesic is in particular in the orbit of the ball of radius r by the action of my fundamental group. So the size of this sigma gamma is at most this r that I have on this picture. That's not so. Then what I want to say is that the size of a deck transformation is the smallest size among all the possible minimal geodesics joining these 2 points. Okay? So given the deck transformation, we can define its modulus and its size. And that's the 2 quantity I need. The 2 quantity I need is I can define the escape rate of my manifold as the limb sup when the modulus goes to infinity of the size divided by the modulus. And this is the key ingredient because we have the following result from Jain, which tells you that if MG is open with non-negative Ricci, and if the escape rate is 0, then the fundamental group is virtually abelian. So the last thing that remains to do is show that using the induction theorem, the escape rate is 0. And I'm just going to claim it. I don't think I'll have the time to go through this proof quite yet. Maybe if you want to ask about it, I can explain a bit more. But let me just move to a quick to the quick open question, and then we can move to some questions maybe. So that's the key to finish. We use the induction theorem, show the escape rate is 0. That's just some calculations, and that concludes the proof of theorem A. So yeah, I was saying open questions. So far, we have only been able to tackle the linear volume growth case. And we were also able to show that the theorems, they fail if you don't assume linear volume growth case, but subquadratic volume growth case. So a question that seems reasonable is, say you take open, non-negative Ricci, and you pick some number delta between 0 and 1. And assume that the volume growth is at most like r to the 1 plus delta. In other words, it is not quadratic. It's strictly less than quadratic volume growth. Then you can still ask yourself the following question. Is pi1 finitely generated? Is it virtually abelian? Moreover, if we assume positive Ricci, is it finite? So that's some of the questions we want to study in the future, but so far haven't been able to make progress on them yet. But yeah, that's hopefully some future problem to be looking forward to. So yeah, I think that's all I want to say. I wanted to keep some time for the questions.
Awesome. Thank you, Dimitri, for the beautiful talk. We'll clap with virtual hands here. Yeah, so actually the drill is coming up, but I don't know, maybe we have time for 1 or 2 very quick questions.
Yeah, sure.
If anyone wants to ask one. Yeah, because I actually have a couple of them. Yeah, maybe I'll go ahead and, and ask. Yeah, so actually with Mauricio Chea, which I think you met before, we were wondering how. So 2 things. So first, how stable is this result, right? Say like in terms of like limits, right? Like say for example, you have Ricci bigger than minus epsilon.
Yeah.
Then can you say something quantitative about the fundamental group? And then I guess the other one is like there's like a lot of papers, I guess from the 90s, where they extend results about Ricci curvature or say positive or non-negative Ricci curvature by admitting that some compact set has other bound, like a worse bound, right? But then since this is like asymptotic, then it
Yeah, I
ends
think
up.
that's a good question. I think you have to see exactly how you want to state how small the curvature is on your compact set, because I think there's these papers by Fukaya and Yamaguchi on
Right.
manifolds with almost non-negative sectional curvature.
Mm-hmm.
And I think that they were able to show that the fundamental groups are virtually nilpotent. But I
I
think the
see.
way they formulate their almost non-negative curvature is that the diameter squared times the sectional curvature is bigger than minus epsilon or something.
Something like this,
So
yes. Yeah.
I think in this particular case, you cannot say better than virtual abilia, virtually
I
nilpotent
see.
in their result. I need to go over it again.
I see.
But
I see.
maybe if you take something even like stronger than this condition, if you take something that's telling you the Ricci curvature is even bigger than their condition, maybe you could say
Right.
something. Mhm.
Right. That makes sense. Because this somehow has to do also with ends, no? Of the
Yeah,
space, right? So this also, if you can limit the number of ends, you can maybe
yeah,
also limit the fundamental group.
yeah,
And
yeah. I think
okay.
that's something they looked at a lot. Yeah, for sure.
Yes. Okay, that's so nice. Yeah, thank you for the beautiful talk, Dimitri.
Thanks.
So maybe one super quick question.
I'm
Juan.
gonna claim the super quick question, if you're
Hmm.
okay.
Yeah, for sure.
Yeah, this is more like an heuristic question. As you mentioned in the introduction, and the Ricci curvature has to do with volume and
Hmm.
distance as well, and you can clearly see this in your results. But my question is, I don't know of any results relating, for instance, higher homotopy groups, which heuristically have. I mean, for an n-dimensional manifold, you will expect that volume is related to the end homotopy group. And I don't
Hmm.
know any results, even in the compact case, that limit
Yeah,
the.
that's a good question. I didn't put it because I wanted to focus on the fundamental group, but yeah, you're right. If you take open manifolds, you cannot say much about the higher homotopy groups. If you take compact manifold, you can say a lot. Uh, so in the case of sectional curvature non-negative, you can actually bound uniformly the total Betti number, and that's a famous result by Gromov. The total Betti number. So if you take a closed manifold by Hodge theory, at some point the Betti numbers are all zero. So you can look at the total Betti number, which is the sum of all the Betti numbers. And if you look at sectional curvature, non-negative diameter at most some big D, then there is a uniform bound on this total Betti number in terms of the dimension and the diameter bound. So that's an important result. There is something like this for Ricci non-negative. There is a uniform bound on the total Betti number as well. However, you also need to have a lower bound on the injectivity radius, and that's a result by Guofeng Wei. So you can also say stuff about the fundamental, but usually you don't quite use the volume. You use something that is called the Bochner formula, and it tells you some. So basically, yeah, when you have non-negative Ricci, you can say stuff about parallel forms. They're going to have to be you can say stuff about harmonic forms. Sorry, they're going to have to be parallel, and then you can bound the Betti numbers, and this is sort of the more what they call the Eulerian approach to Ricci curvature, or like
Yeah,
Mongian. I always mess them up. Like I never
I'm
remember which one
I'm
is
more or
which.
less familiar with those results, but
Okay.
yeah, I was thinking more like in the direction of pure higher homotopy groups. I'm saying like
Yeah.
something that, I mean, they are abelian. Okay, we know that, but
Hmm. Yeah.
apart from that, can you say something stronger about the?
Yeah, that's a good question. I'm not sure. I don't know, to be honest. I think that's
Yeah.
something they study a lot with more like a minimal surface theory, when like
Mm.
maybe your pi2 is non-trivial and you want to look at minimal surfaces that represents classes maybe in your pi2, like minimal spheres. So I know
Yeah,
that's
yeah,
a problem they study a lot in minimal curvature, but I haven't seen such results quite yet
yeah. Me too.
in Ricci curvature.
Me too. Me too. But well, I guess we're almost about to run. So thank you
Yeah.
for your
Good
beautiful
luck,
talk.
guys. Hope you
So,
make
by
it.
the way, just very quick, Dimitri. So there's an option. So I guess I'm sure we all enjoyed your talk very much, and many of us would like to see like the full proof or the full slide. So if you want to come up again for a second lecture, like a second part lecture, this is also possible, but you'll let me know in
Oh
an
yeah,
email.
I'd be happy. Yeah, something I just skimmed through is it was not really clear to me before I met Jain why escape rate 0 implies virtually a billion. And I had a
Right,
lot of
right.
slides. I had a lot of slides on this. So if you want to hear more about the story, I think there is something that's quite important there. I haven't had the time to explain today,
That
but
would be
yeah,
great. Yeah, yeah. So let's schedule it. Yeah.
sounds
Right.
good.
Well, thank you very much, Dimitri. So
Thanks
for
everyone.
the beautiful talk, and see you guys on the next one.
Bye. Thanks.
Cheers.
Gracias.
See you guys.
Gracias.